Title of our presentation: Pipeline Durability and Integrity Issues at Hydrogen Transport via Natural Gas Distribution. Dr. Olha, Zvirko, Oleksandr Tsyrulnyk, and Halyna Krechkovska are from Karpenko Physico-Mechanical Institute of the National Academy of Sciences of Ukraine. Dr. Leonid Unigovskyi from organization Naftogaz-Bud Informatika, also Ukraine. Plan of the presentation: Introduction, general regularities of degradation of long-term operated pipeline steels, hydrogenation sources of pipe from internal surface, operational damaging as the main factor of the negative hydrogen influence on pipe integrity, peculiarities of the experimental studies of the influence of natural gas hydrogen mixture on an integrity of pipes, and concluding remarks. Introduction. The new trend is now to use hydrogen as fuel in industry, and it causes some challenges in the different aspects, namely hydrogen transportation. Hydrogen transportation is a cornerstone for setting up a hydrogen-based economy. Using the existing natural gas pipeline network for hydrogen transportation could be a way to match hydrogen economy needs and today's possibilities. As you can see from this data, some hydrogen pipelines exist, such as networks owned by Air Liquide in the USA and the Northern Europe. However, there are currently no large and widespread national hydrogen grids, and building them would require huge investments that can only be motivated by large hydrogen demand. So, supplying hydrogen by blending it with natural gas using existing natural gas infrastructure could be considered. The Natural project is the first step in assessing the potential of the existing natural gas network for hydrogen delivery. Ukraine has an extended network of natural gas transit pipelines that could be used for supplying hydrogen as well. However, during long-term service, pipeline steels can degrade. A significant decrease of mechanical properties of operated steels, mostly brittle fracture resistance, can finally cause structure failure. Embrittlement. Deterioration of mechanical and corrosion properties is often the result of in-service degradation. Based on our previous results, we can distinguish two stages of in-service degradation of low carbon and low alloy structural steels. Stage 1, deformation agent, and stage 2, in bulk materials damage accumulation, or so-called dissipated damaging. It is well known that under strain agents, the strength and hardness increase, and persist and resistance to brittle fracture decrease. However, this tendency of mechanical properties changes could be violated if the metal undergoes in bulk multiple damaging during operation. In such circumstances, strength and hardness of the damaged materials decrease, but elongation increases. Further operation of the degraded steel leads to additional decrease in reduction in area and characteristics of brittle fracture resistance. Our preliminary study showed that the model medium of water condensate on internal surface of gas pipelines has served as a source of hydrogen due to the electrochemical corrosion. The same situation should be also in the case of gas-hydrogen mixture transportation. Then, hydrogen in atom state evolved as a result of electrochemical reaction and molecular hydrogen dissociation as well, can be absorbed by pipe metal in atom state, which can migrate via pipe wall. From another hand, operational damage serves as the main factor of the negative hydrogen influence on pipe integrity. Still, hydrogenation together with working stresses facilitates a development of in-bulk damages at nano and micro scales. It's often the main reason of degrees of brittle fracture resistance characteristics of materials under long-time operation. Here you can see some example of revealing of damage accumulation by mechanical loading. Namely, you can see in bulk pipe wall dissipated damaging on fracture surface after impact strengths and usual tensile test of specimens. And you can see as preliminary cathodic hydrogenation accelerated micro damaging. And one important should be noted, more intensive damaging is the rolling direction. Therefore, specimens cut in transversal direction to pipe axis should be more sensitive to operational degradation. So, regarding the peculiarities of the experimental studies of an influence of natural gas-hydrogen mixture on an integrity of pipes would be like to draw the following. Firstly, to prefer transversal specimens as the most sensitive to hydrogen-induced cracking. And secondly, if we consider a possibility of metal hydrogenation, we should prefer thin thickness specimens. The next peculiarity is as follows. A holding of specimens in pipe with gas-hydrogen mixture under preliminarily controlled tension with fixation of stress state. Here you can see the device for such a procedure, which enables to tension some specimens and gather it in the special block for placing inside in pipe for holding the certain time, in months and years. It is predicted that thin specimens during so long-term time will be noticeably hydrogenated if such internal in-pipe environment can hydrogenate still in principle. We should also remember that hydrogen can leave a metal after putting out of specimens from pipe with gas-hydrogen mixture. So we plan to serve specimen in liquid nitrogen before the next tests. Our program of tests predicts the most important studies, namely hydrogen-induced cracking tests, fracture toughness tests, the integral method, Sharpie tests, hydrogen concentration measurements, electrochemical permeation methods for evaluation of hydrogen diffusivity in metals, and microfractography analysis for estimation of the influence of hydrogen on micromechanisms of steel fracture. The known method of hydrogen permeation should be especially useful in our case, since this method allows to study some important parameters caused by holding of specimens in pipe, a change in hydrogen trap intensity due to development of damaging, a measure of so-called critical cathodic current density for pipeline steels. This parameter can serve as parameter of a sensitivity of steel to hydrogen cracking, less level of critical current, more sensitivity to hydrogen cracking. And finally, some concluding remarks. Carrying hydrogen or its mixture with natural gas via steel pipelines can lead to hydrogenation of steel from internal pipe surface due to both hydrogen dissociation and hydrogen evolution under electrochemical corrosion as a result of interaction with condensed moisture. Absorbed hydrogen can negatively affect on steel by both hydrogen environment and creation hydrogen pressure defects as a result of recombination causing dissipated damage. Operational degradation of pipe steel decreases significantly the characteristic of brittle fracture resistance, including hydrogen-induced cracking. In bulk dissipated damaging is the main reason of a sensitivity of degraded steel to hydrogen embrittlement. And finally, the main peculiarities of experimental studies of influence of hydrogen natural gas mixture on pipe steel durability. Comparison of mechanical behavior of as received and exploited steels. Evaluation of characteristics of brittle fracture resistance and hydrogen-induced cracking. Holding of preload specimen in hydrogen natural gas mixture with the next prevention of hydrogen desorption before tests. Determination of hydrogen concentration, hydrogen permeation, microfracturography, and thank you for your attention.